Hello everyone and welcome to another video for Elephant VFX Patreon feed. Today we're going to be talking about BEX. This is the second video of the series Introduction to BEX. Actually, I shouldn't call it a series because this is going to end here. I'm not saying that I'm not going to make any more BEX related content. Most likely that wouldn't be the case. But this is not a series, so this is just a quick introduction to BEX, and that is only made of two videos: the video that I posted before and this video now. That I feel that it's gonna be about 3 hours long or something like that. Let's see. That's my hope, at least. Again, I don't want to make any more videos anytime soon about BEX. So I want to fit everything into this video, even if it, if it becomes something very long. Hopefully it won't, but definitely more than 2 hours. All right. So this week, or in this video, we're going to be talking again about BEX, but I think I'm gonna mix it with some type of simulation, right? Because we've been using BEX for manipulating components, manipulating geometry and colors and different attributes, but we haven't used it that much in simulations yet. So, let's make a couple of particle simulations. It doesn't really matter. I just want to have something that involves simulation in Houdini. And then I can show you that we can actually manipulate simulations also using BEX. So I think that's going to be cool. And then, I'm planning to do a couple of different exercises related with that. And at the end, we're going to do another exercise, which is, it involves more complex BEX expressions. Some of those require probably some knowledge of maths that I don't even have, to be honest. I just know how to mess with that a little bit, how to type that code for those BEX expressions. So it's not that difficult when it comes to handling everything related with BEX behind those maths. But if I need to go deeper into explaining how those matrices work and all of that, honestly, I'm not the right person to do that. I don't really understand maths very well. My background is in fine arts, so that's a little bit out of range for me. But if you understand maths, well, then much better. You will know much better how to write complex BEX code. But anyway, I will show you 3 different examples today, 3 different exercises that I believe, even though they are simple and the code itself is very simple, I can relate to these exercises because they are, I'll be showing you stuff that we actually do in production. So even if it's simple, they are things that you're going to put in practice anytime soon. And that's the good thing about BEX. It doesn't have to be complex. Okay, it can be, most of the time you're adding maybe a couple of wranglers and each of those might have 1 or 2 lines of code. That's it. That's the type of BEX that you use on a daily basis. You don't create huge, huge BEX codes and hundreds of lines. That's usually not the case. Okay, all right. So we're going to jump into the first exercise, which again is going to involve some kind of particle simulation. So I'm going to start by creating just a sphere. Let me dive into this sphere. And let's make it, it doesn't really matter, but just to make it a little bit more, when I use a primitive as a source for any kind of particles or whatever, I tend to use polygons because, the distribution is more uniform, right? So if you take a look at this and you take a look at this, this is more uniform. So if let's say if we are emitting from each of the points of this sphere, it would be better just to have something that is very uniform, so you don't emit, like a lot of things from here, but less from here. But that depends obviously on what you're trying to do. All right, so I'm gonna choose this polygon sphere. Let me add a transform here and move it up a little bit, something like that. Okay, so this is 5 units up. Okay, and I'm gonna create a pop network. Pop network, there you go. And if I go inside, everything is done automatically here. So I have my pop source, a merge that is not merging anything, but if you have other forces or whatever, you would merge them here. You have your pop object, pop solver, and the output, right? So maybe I can change my background to be dark and get rid of this grid, so it's easier to see. Okay, so we have this sphere with some points, and if I press play, I get a simulation, right? So basically the sphere is being filled by points. Let me set this to real time, and this is what we get. And of course, that is being established by the pop source. If you go to birth, you know, this is the constant birth ratio or rate. So obviously, if I add another 0 there, then we would get even more particles, okay? Just regular pop stuff. All right, I'm gonna set that one back to 5,000 points. Okay, this is as simple as this, right? Of course, you know, nothing really happens here because we don't have any extra forces. So let me add a gravity. So by adding a gravity, if we press play now those particles are falling down. And as you can see, they are falling down almost infinite. I mean, not really infinite because that is being defined by the life expectancy, that is 100. This is in seconds, right? If you leave your mouse there, it will tell you how long the particles will live in seconds. So that is 100 seconds. So of course, you know, we would have to wait 100 seconds to see this particle size, which is something that we can change soon. Okay. If we change this to, let's say, 1, now these particles will live for 1 second, right? And then they start dying. Everything is very uniform because we also have these life variance set to 0, so we can give it a little bit of variance. So if we set that one to 0.5, this will mean that some particles will live for half a second and some of particles will live for maybe 1.5 seconds. So there you go. And now we're getting, you know, something a little bit more random. Okay, cool. I'm gonna set this back to the default parameters because you wouldn't be tweaking this from here. Generally speaking, you would create your own controls and you would have, you know, more customization over all of this. And that's when pop wranglers come into the game, right? So yeah, let's do that by wrangler so we can actually experience a little bit of pop wrangling. I'm gonna move this here and I'm gonna create a pop wrangler. Pop wrangler. We haven't seen this one before, but you know, it's basically the same. It's just a wrangler, but in this case, it lives in the pop network, right? So there is no different than, it's not that much different than creating a point wrangler. You still have your Bex expression field here where you can type your code. But again, it lives inside of a popnet. Okay. All right. So if we want to target any of these attributes that we see in pops, you know, it doesn't really matter if it's source, birth attributes, whatever. So any of these attributes can be used in wranglers. And the good thing is, like, we don't have to create them. They already exist. We just need to invoke them, right? We just need to call them. So if I, let's say that we want to change this life expectancy value that I have here that currently is 100 seconds. If I leave my mouse there, it's going to tell me the name of the attribute. And as you can see, the parameter is called life. So this life expectancy is life. If I want to use that in wrangles, I need to invoke the parameter live. If I want to use this one, it's called live bar. If I want to use seed, it's basically seed. If I want to use that one over there, is the name of the parameter is constant rate. Okay, so let's call that parameter. It was called live. So at live equals to whatever I want. So if I say, let's say 1, this will live for 1 second. Okay, let's do something a little bit more complex. So live is going to be equal to, I'm going to fit it in a range. So fit 01, we know this very well. And now we're going to say a random function based on ID. Okay, let me close that for a second. This is gonna break, but don't worry, I just want to explain something here. In simulations, we never use ptnum. Remember that before we were relying a lot on ptnumber, which is the points of the points where you want to run this wrangler, this expression. We don't do that with simulations. And the reason being is because, let me disable that, and let me enable perhaps the point number here. You can see the point number is changing all the time, right? And the reason that it's changing all the time, it's because these particles, they are being born and then at some point they die, right? So when a particle dies, it loses that PT number, and that PT number gets assigned to a new particle that is being born, right? So if we run something over PT number here in BEGS, it's going to break at some point, right? Because it's running over a point, and all of a sudden that point disappears, and that number gets assigned to a different point that is being born, and everything will break. So we don't use PT number with simulations. We always use ID because the ID doesn't change. And the good thing about ID is that in simulations, the ID gets created automatically, so we don't have to create it. I don't know if you remember, but in the first video, we did something similar with the scattering system, right? I was showing you how to make this forest, and at some point I was deleting the scattering system or some points of the scattering system based on PT number, and things were changing because we were reassigning those numbers. So I showed you how to create an ID for each of the points, and then we could easily modify the scattering system without losing the assignments because we were doing it based on ID. And because ID doesn't change, nothing breaks, right? So it is the same philosophy here. But again, the good thing here is like we don't have to create that ID. That ID, it gets created automatically when, as you can see here, there is an ID attribute here that gets created automatically when we run a simulation. So that's good. So again, don't do PT number, always target ID when you're dealing with simulations. Okay, cool. So the live is going to be a random function that we're fitting between 0 and 1 based on the ID. And now we can assign, instead of 0 and 1 to that fit of 1, we can assign values. So we can basically create a channel float that we can call, for example, minimum, and another channel float that we can call maximum. Okay. All right. So if we do that, and now we create those spare parameters, now we have a minimum and a maximum. So let's assign some values here. So let's say the minimum value should be, I don't know, whatever, 0.1, and the maximum 1.5. So if we do that, now we have a live expectancy of these particles that goes from 0.1 to 1.5. Okay, if I say 3 there, then we would have some from 0.1 to 3 seconds. So we get more variations, okay? I had 1.5 before, and oops. And I think this was decent, okay? So this is another way of creating variations. And again, you don't really want to just play with life expectancy life variance. It's better to create your own controls. And here, this is very simple, but most of the time, this is the only thing you need. But of course, you can add whatever here, right? You can add seeds, you can add whatever you want in the way that I showed you in the first video. Cool. We can also, something that I do is, generally speaking, I do always these, but I also add a ramp distribution, so I can favor more the minimum or the maximum, because right now we have a random interpolation between minimum and maximum, but we can favor more one or the other. And the easiest way to do that, in my opinion, is just with a distribution ramp. So what we can do here, we can say fit01. I can say I want to create a channel ramp, okay, that I can call whatever. I'm going to call it ramp, okay, and then I keep the rest as is. I'm missing a parenthesis there, right? And now I can create that ramp. So now I can favor more towards 1.5 or towards 0.1, right? So if we do something like that, we're getting, something like that, or, we can do let's say something like that, and we will get like, right now everything is favor 0.1, or we can do the other way around. I can do something like this. Whoops. And now most of the points will leave for 1.5. And you can create any type of distribution here. So let's do something. Something like that. And now, as you can see, we're getting a very nice variation here. Okay, great. All right, let's do something more elaborated. So I'm gonna go here, and before this popnet, let me do something. If we take a look at the normals here, this is the normals that we have. Let's emit based on these points. So we can do a normal here. We can run this over points. And now we get that. So every point has a normal pointing out. You can do that. You can also do a facet and click on pre-compute normal. And that will give you the same thing, right? So there are two ways of doing this. Okay. So now I have these normals. Cool. Something very common in simulations is to use the normals to create velocity, right? Because right now, if we take a look at this, this is what we get. Let me do one thing here. I'm going to disable the gravity just for a second. So right now, this is what happens. There is no velocity. That's what the particles stay in place. They just try to fill the volume. And when we had the gravity, they are falling down because the force is being applied over those particles. But right now we don't have any velocity. Let me create a point wrangler here. And I mean, we can basically assign a velocity if we wanted to. We can say velocity is equal to, and velocity is a vector, right? So we can do something like 1, 0, 0. We can do something like that. And when we press play now, because they have some speed, some velocity, they are basically going towards that axis. Or we can do this and they will go up, right? And of course, well, let's actually put 10. So they have a lot of inherited velocity, so they go up quite a lot. Of course, if we enable back the gravity, now they will have to fight the gravity, so they will go up. Right now, they start falling. The velocity is too high, so it's probably too high for the amount of gravity that we have. But if it's less, as you can see, they try to go up, but the velocity is not strong enough to fight the gravity. Okay, let me disable the gravity again. But because we created these normals here, we can actually use this information and pass it to the velocity. So if I say that the velocity is equal to the normals, right? We can actually see the velocity by clicking here. Point trails, we should be able to see it, but I think there you go. You can see them there, right? So right now, the velocity is based on these normals. So what's gonna happen is that each of these points is gonna travel into the direction of the normals. So if we press play, this is what we get. This is a very, very common practice to manipulate the velocity based on the normals. We do this all the time, or FX people do this all the time. Cool. So now we have something that looks quite cool. Yep. Of course, if we go back and enable gravity, same thing. This velocity will have to fight the gravity. So, they try to go out, but they get pulled by gravity. All right, cool. Let me again disable gravity and let's keep manipulating the velocity. Let me save this. All right, so having this velocity here, we can also have some kind of extra control, so it doesn't rely only on the normals, right? So let's say we want to push these particles even more. Well, we can create a control here to take care of that, right? So if we say, because we're manipulating the normals all the time, let's say that the normals are multiply or equal by custom control. So let's create a channel float and let's call this one, let's say multi or something like that. So by doing that, if we now create that spare parameter and we set that one, let's say to 5, right? Now we have more velocity, right? We can check the velocity there, right? Or if we say 10, we would have even more. There you go. So I don't know, let's set that one to something like 5 and let's enable gravity again. And now there you go. Now they are being pulled down by the gravity, but this multiplier here is taking care of, pushing them outwards even more. So, they go out and then they fall because of the gravity. Okay, great. Let me go here again, disable gravity. Let's control a little bit more the velocity. So the velocity is looking nice. It's nice. It's responding with this inertia. So it's working okay. The only issue that we have now is like they are all moving at the same speed, right? They are basically moving at 5. That's the speed of the velocity. So we can add a little bit of variance between the velocity, and we know how to do that. We've done that many times. So let's mute that one for a second and maybe do something like the normals are let's say multiply or equal, and let's create some random controls. So again, we can do a fit01. We can use a random function and we can run this over PT number. Now we can run over PT number, right? Because we're running over the points that we're using for emission, which are always the same because this is a sphere. We're not running over the simulation, right? We're kind of running over the primitive. So we can run over PT number. We don't need to use ID there. We could, but it's not really necessary. So let's create a channel float for the minimum velocity. So we can call this min vel, for example, for minimum velocity, and then we need another channel float, and we can call this one max vel. Okay, and where did I make a mistake here? Let me fit 01, run PT number. Okay, we have a channel float. Okay, why am I blind? I made a mistake, but where? At normal, multiply equal, fit 01, random PT number, channel float, min vel, channel float, max vel. Okay, I don't see the mistake. Can you see the mistake that I made? Because I can't. I'm sorry, I'm completely blind now. Normal, fit, let me go. I mean, definitely the mistake is here. Was that an update issue? Hopefully, I don't think so. Yeah, it was an update issue. Anyway, yeah, sometimes that happens, like it gives you an error. Then you go one level up, or you select another node, another one, and then it fixes the issue. Anyway, so let's create those values. So if we say something like, I don't know, minimum 1, maximum 4. Let's do something like that. So if we play, there you go. So now we have some of them, they are moving at speed of 1, some of them at speed of 4. If we say both, if we set both to 2, for example, that would be the same velocity for both. If we do 0.1 and 2, for example, some of them are moving at 0.1, some of them are moving at 2. So I don't know. I said 1 and 4. This gives me enough variation. So it seems to work just fine. Okay, cool. Let's see how it looks with the gravity. Okay, and we get something like this. All right, I'm happy with this. I mean, it's not that complex, but I'm okay with that. So let's pretend that this is some kind of cannon or pistol or laser or whatever that is throwing bullets into something else. So let me do this. I'm going to duplicate that sphere. I'm going to template that one and look at that one. Okay, so let me create another transform here, and I'm basically creating a target now. So we basically shoot at something, maybe -5. There you go. Okay. All right. So let's again, this is our cannon. So let's pretend we're shooting to that sphere. So I'm gonna put this here, and maybe I'm gonna add another transform. And I'm gonna set that one to rotate automatically based on timing. So the pivot point of this transform obviously is in the origin of the scene, so now it's very easy to just rotate around that sphere. So we can set this one to time, and now that sphere will move. Well, of course, it's moving very slow. So let me multiply this by some kind of value, 75. Yep. So now now this sphere is kind of moving around that one. That's cool. So let's shoot at that sphere, right? Let's aim this to point to that sphere that is moving around. Okay. So how do we do that? I kind of showed you how to do that in the first video already. Not exactly this, but something very similar, right? So let's create a point wrangle, and that's using the bbox function, right? So I'm gonna connect this one here, and I'm going to connect, actually the other way around. We want to change the normals of these normals that we have here based on that. So let's connect this one to the first input and that one to the second input. And what we can do now is we can say the normal is equal to the point of the second input, this one here, which is 1, right? Remember that this is 0, this is 1. So we want to point to 1 based on the position, and we just need 1 point, and we need to subtract itself. So minus position. There you go. So if we take a look at that, there you go. Look at this, this new normals, right? So we went from here to there. And if I press play, if I template this thing here, you can see that we are always pointing towards that sphere. So that's pretty good. Okay, that's great. The only issue is that, now we don't have the randomization we had here. We created this randomization there, so we would have to do kind of the same here, because otherwise, this is very, very uniform and boring. So let's do basically the same. We can just copy that or just type it again so we can actually practice. So I'm gonna say that the normal that we created is multiplied or equal, and let's do the minimum and maximum again. So I'm gonna do a fit01. We need a random function based on the PT number. We need a channel float that I'm gonna call minimum, and another channel float that I'm gonna call maximum. There you go. Cool. Let's create those. Well, let's add the multiply and everything else. So another multiply equal. So basically the result of these two lines, we want to create a channel float that I'm gonna call multiply. Multiply. There you go. And finally, I want to convert all these normals into velocity. Exactly the same thing that we did before. So the velocity is equal to the normal. All right, let's create that. Let's take a look at the normals. So before we said 1 and 4, I believe, right? So let's do that. Right, 1 and 4. Okay, and the multiply to 1. So that's basically what we get. If we increase that one, we would get even more. This might be too much, I don't know, 0.1, there you go, and 2. So now we're starting to get that variation, and then we have this to play with. I don't know, let's find something that you like. Let's say that. So now we get that. All right, cool. So yeah, this would be basically the velocity, right? Okay, so if we ignore this one for a second, right? And we connect that one there. That's what we get. Okay, so basically we're trying to shoot that ball. Let's template it. But of course we have the gravity playing its part here as well. But that's cool. We're trying to chase it. So that's fine. That could be like a cannon in a spaceship shooting another airplane or another spaceship that is flying around or whatever. Right. Let me increase the amount of particles. So I'm going to go here. I'm going to go to my source first input, and I'm going to give it, I don't know, an extra 0. So that's 50,000 particles now. There you go. Cool. One thing that maybe you notice here is this banding or stepping, right? That is because of the resolution of the simulation. So if we go again to the .NET and we go to the pop solver, we have these minimums of steps. I'm going to increase that one to something like 3 or 5. And now there you go. And now that is not that visible anymore, and we could go even farther, like 5. Of course, it will make everything a little bit slower, but now it looks much better. We don't have that stepping anymore, or that banding, or whatever you want to call it. Okay, cool. So we have our system working. What else can we do here? There is a parameter in any simulation that is called age, right? And that is basically the age of the particle, meaning that when the particle is born, it would have an age value of 1, and when it dies, a value of 0. We can use that attribute for many things. For example, we can use it to color these particles, right? We're going to see a couple of ways of coloring particles in a minute. So here, let's create another point wrangle, and we can say at CD is equal to whatever vector, right? So if we say 1, 0, 0, we do that. Now our particles are red, of course, right? But again, we can use the NH attribute. So we can say itself minus NH, and now the particles are white, and when they die, based on the NH attribute, they would be black. As you can see, right? So they are getting super bright when they are born, and then they are transitioning from white to 0. So they, at the end, they just become black, right? So this is very common, and this is one of the attributes that you will pass to the LookDev people to work on the shaders. We can use it for other things. Well, actually, we're going to use it later for something else. Let me actually add a collider here. So I'm going to go here, and I'm going to create ground plane. Or actually, you can do that, or you can create your own collider. So yeah, let's do our own collider. Why not? So I'm going to create a grid. Okay, I'm going to make this big enough. So I don't know, like 40 by 40. Give it a little bit of this. I'm going to add a null. And I'm going to call this one out collider. There you go. Cool. So now inside of the PopNet, we can just add a static object. Let's point to the collider. And in collisions, I'm going to set this one to surface collisions. There you go. And let me add a merge. Pipe that one there. Put the collider first. There you go. And see if this is actually working. I'm going to give this a color, because it's too bright. Something like that. All right. What's going on here? Oh, the PopNet is exporting all the objects, meaning that it's exporting not only the pop object, but the static object as well, right? That's where we see the grid there. So you can basically type *pop, and that will basically get rid of anything that is not a pop object. So now this works better. And if you want, you can merge these two to see them together. So if we press play, there you go. Now this is bouncing, right? It's not going through the thing, and it's bouncing. If I stop this, you see that this is bouncing, but it's all bouncing to the same level, right? And that is because we have bounce, and we have friction, and we have other attributes affecting the physics of the simulation. That is also something that we're going to change in a minute using wranglers. But this is all working. That's great. Let me go to the pop source. or actually in the Pop Wrangler, where we created this, let's make this to live a little bit longer, right? So instead of 0.1, I'm going to say maybe 0.35 and I don't know, 2.5, something like that. Let's see how this looks. Cool. So now they live for a longer period of time. I think I need to make my grid a bit bigger. I just wanted to have particles living longer so we can actually see a little bit better the bounciness. So yeah, basically they hit the surface, they bounce, but yeah, if you look here, this is a razor sharp line. Like they all bounce and at the same height, basically. So let's see how we can change that. Back to the PopNet. Let's do one thing. We can add a pop force in the first place. And this one, you know, this one has options like amplitude and roughness and turbulence and, you know, that kind of thing. You can keep it like that. You can keep it just as default. Let's see how this behaves. Okay, so nothing really changes that much in terms of how uniform this thing is. But of course, here we can add like different changes, whatever. But let's don't mess much with that. I just want to have these forces here. But now we can manipulate all of that. We can add a pop property. Okay, and this pop property, if we place it here, we can enable the bounciness. So let's say 3. So now all of these will bounce quite a lot, right? There you go. So, whoa. So now this is bouncing this high. Again, everything is uniform because everything has the same value. But here is how you can change it, right? So 1 is the same that we had before. How can we modify that? Well, first of all, if you leave your mouse there, it's going to tell you the name of the attribute, as we've seen before. The name of this attribute is bounce. So now we can refer to that in a Pop Wrangler. Or if you don't want to create a Pop Wrangler, as we did before, in some of the nodes, you have this use Bex expression. So when you enable this, you actually get a Pop Wrangler here. This will be the same than creating a Pop Wrangler, piping it here, and say, bounce is equal to 10. You can do that if you want, but you can do it here as well. You can say that bounce is equal to 10. Okay, and if I press play now, boom, things bounce like crazy. Okay, so let's not do that. So I'm going to say that bounce is equal to some kind of randomization that we already know how to make. So I'm going to use a fit01 random function based on ID because we're in a simulation. Let's give it a seed. So I can say, I can create a channel for the seed or just specify a seed here. And then I can create those spare parameters, a channel float that I'm going to call minimum and a channel float that I'm going to call maximum. There you go. And of course I made a mistake. Where is the mistake that I made? Fit01 random, this is all good. Channel float minimum, comma, channel float maximum, and I'm missing a parenthesis. That's why. Okay, great. Click here, create the spare parameters, and now we can change this. So I'm going to say minimum 0.2, for example, maximum 1. Let's take a look. There you go. So now we are getting some variation, right? So some of them are bouncing more, some of them are bouncing less. Cool. If I set that one to 2, it should be pretty clear now. There you go. Like some are bouncing very little, some are bouncing a lot. Okay. I'm going to go back to 1. Yeah, I mean, that looks quite cool, right? Nice. Cool. So now we have plenty of control, right? Over the variance of life, over some of the forces like bounce, but you can add any other force here. I just want to, show you how to do it, but of course you can play with all the settings, all the parameters there if you wanted to. Okay. If we go to the pop solver, because right now we have these the control of the color of the particles being controlled by the age that we're using here. That's cool. I mean, again, that's one of the attributes that we usually send to LookDev, so they can play with that. Another attribute that we always send to LookDev is some kind of heat attribute, meaning that these particles, when they hit a surface, maybe we want to give them an attribute so they can color the particles based on when a particle hits something. Because maybe, you know, these are sparks, and when a spark hits something, it also dies or changes color drastically. So we can do that as well. So here inside of the PopNet, if we go to the pop source, we have this collision behavior tab. And here we have this add heat attribute. I think by default it's already, yeah, it seems like by default it's already enabled. And that parameter is called heat attribute, but actually if we click here, we can see many attributes related with heat. So we have, for example, heat normal, heat number, heat path, heat position, heat primitive, heat time, heat total, heat UV, heat V, heat velocity, and whatnot. So we can also modify those attributes with Wranglers, right? So let's do that. Let's move this up a little bit. And I'm going to add another pop Wrangler. Cool. And pipe it here. Right. So what we can do here, we can introduce a conditional, for example. So we can say if at one of those heat parameters, heat number is bigger than 0. Okay, because let me ignore that for a second. So if you check your attribute geometry spreadsheet, right, and you go to the pop object and then the geometry, here we should have a heat number that is 0. We don't have any ones, right? Because we haven't hit anything yet. If we advance the simulation, now we should have a heat number attribute that is 1, right? So we have a few ones because we are hitting. We're hitting that. We're hitting the collider. So we can use that here. So again, we can say if heat number is bigger than 0, meaning that it has collided with something. Let's open the conditional. Let's close it here. We can say that CD is equal to whatever. So I'm going to say 1, 0, 0, something like that. Okay. So now when a particle hits the ground, it's going to be red. Let's see if that works. Let's take a look here. Of course, we cannot take a look here because here we're overriding the color, right? Or, well, we can just disable that. So now, there you go. When we hit the surface, the particles are turning red. Okay, again, something very common we do all the time. Right. What else can we do here? Let's actually make this into something that we can render properly. So I'm gonna move this aside for a second. Yeah, let me get rid of all of that. I'm gonna create a copy to points. I'm gonna set this one to pack an instance. I'm gonna connect this one to the points that I wanna copy. I'm gonna move this over here for now. Let me create a sphere, connect that one there. There you go. And now we have these spheres being instanced in the points. So when we press play, that's what we get. Of course, these are a little bit big, right? So we might want to change this to, I don't know, 0.1, and then we get something better, hopefully. And as you can see, this is super fast because we're using packed geometry, so this is super efficient. Okay, that's cool, that works, but it doesn't look very nice. what else can we do here then? Well, let's change the scale of that sphere, right? Let's go back to 1. And or well, any size that we use here, they are all the same size, right? So we don't want to do that. So let's change that. How can we change that? Well, we have a few ways of doing that, but of course it's going to be with Wranglers, because this video is all about Wranglers. Let's add a point Wrangler, pipe it here, and let's change the scale. So we can say p scale is equal to something. So as usual, the first thing that I do is adding my, fit01 values. So fit01 random based on, you guessed it, ID. We need a channel float that is going to be minimum, channel float minimum, channel float maximum, and let's close that. Okay, let's create that, and we can say 0.1 and 0.4. Of course, the 0.4 is still too big, so let's do 0.05. Is this actually working properly? Fit01 random ID, channel float minimum and maximum. Yeah, it is working. It's just like they are just too big. Okay, yeah. So you can see that, yeah, you can see it here very well. Like we have something small based on that and something bigger based on that. So, maybe this is good enough for you. Maybe this is a good variation, and you know how to create a ramp to favor one or the other. I show you how to do that here, right? So do that if you want to. Instead of this, I'm gonna get rid of that one and create another point Wrangler, because instead of this, what I want to do is, remember this H thing? Let's use that one, right? So I'm gonna enable that one again. So now we can see how particles become, black when they died. Oh, I think my dog is dreaming with something. Oh, must be an exciting dream. Okay, so let's use this NH thing that is currently living in the color. So let's do that. So I'm gonna go here and I'm gonna say the P scale is, oh, actually I shouldn't have deleted this, because maybe we can use that. Okay, so I got this one back because maybe I want to use it. Why not? I'm going to enable this again. So let's do 1 and 1. Okay, so this is what we have. So what I'm going to do here is, keeping what I had before, P scale is multiply or equal. And I can clamp this, right? Because basically I want to use this color, right? So I'm going to clamp it so it goes from 0 to 1. And then the only thing that I want to use is the red channel. Right, because particles go from red from white to black in a grayscale fashion, but grayscale is only the red channel. So let's use that here. Let's say I want to clamp it so it goes from 0 to 1, and then I want to use I want to use the CD attribute and only on X, right? And then I can give it some values to that. So the smallest value is going to be, if I leave it like that, the smallest value is going to be 0 and the biggest is going to be 1. But I can remap it. So I can say the smallest one is going to be 0.2. So we don't have a sphere with a value of 0, right? And the biggest one is going to be, let's say, 1. Cool. So when we do that, this is what we get. But of course, we need to play with this a little bit more. So let's say 1 and 0.1, no, sorry, 0.1 and 0.05, something like that. Okay, so now, so we make it a little bit bigger, 1 and 15. There you go. Yeah, this works quite well. So now we can see that we're using this multiplier, but we're also running it over the age attribute that we created before. So when the particles are born, they are as big as they can be. And when they died, they are quite small. So this is also very common, right? To make particles smaller with age. Cool, that looks nice. Right, the only thing is that now we lost the heating attribute, right? Because we are basically, I mean, we didn't lose it, we have it here, right? So they are becoming red when they heat something, but because then we are creating this CD over age, we're overriding that, so we lost that here. No problem, we can bring it back very, very easily. So we can basically move this aside, and because that attribute lives here in the .NET, we can just pipe this one to the second input of this point wrangler, right? And that's pretty much what we need. I mean, now we need to bring back that thing. So here, what we can say, we can do it in a different wrangler or in the same one. We can say the CD is equal to point of the input what? 1, right? Because it's the second one, 0, 1, 1. We need the CD parameter on the PT number, on the points, right? So if we do that, this should work. Let's play it. Yeah, and it does. So now we have the best of two worlds, right? We're using the NH to control the size of the particles. And then we're using the heating attribute to control the color of the particles when they hit the surface. Great. All right. What else can we do here? We're basically finishing this first exercise already, right? Let's say, let's add more particles. Can we add more? So let's add 100,000 particles. Is that going to be fast enough for my computer to play with? Yeah, I mean, it's not terrible. Okay, cool. I mean, it's super fast, right? I mean, you can cache this in a minute. But of course, to play in real time, it might be a little bit slow. No, this is totally fine. Okay, so let's say that we want to add a global control for culling particles, right? For basically reducing the amount of particles after the simulation, I mean, right? So let's say we have this, and let's say this is rain and it's falling on something, and, you know, we do the simulation, and after the fact, we say, oh, this is maybe too many particles. It would be nice to have half of the particles. Well, instead of doing another simulation and waiting time and all of that, we can just add some kind of calling system with wranglers. That would be very, very simple. So let's add another point wrangler. And what we can do here, we can create a function that is a float function that we can call whatever. I'm going to call it points, for example. And it's equal to a random based on ID. We need a seed plus 1, 2, 3. That would be my seed. And we can say if that points float function is bigger than a channel that I want to create, a channel float that I can call, let's say, threshold. Okay. Let's close this. Let's open the conditional. I can say if it's bigger than the number, remove the point on the first input based on the PT number. There you go. So let's enable this. Let's bring back this to 1. So now we're not really removing anything, But now we can remove based on this. So if I start reducing this, it's going to reduce the amount of particles after the fact, right? After the simulation, this could be a cache. So yeah, if I want half of the particles, I put this one to 0.5, and now I have half compared with that. If I want just a few particles, let's do something like that. And you know, the randomization is based on the ID, so it's already pretty random. So we can have something like that. Cool. And this would be the rain falling wherever, and you know, it looks nice. Oh, we want way more. No problem, sir. 0.4, and now we have way more rain. All right. So yeah, just another useful thing that I use all the time, this kind of culling thing. So, you know, I can create wedges based on this after I simulate a lot of stuff. You know, I tend to, especially when doing particles, I tend to do always way over the top, so I can always go back without simming again. I do this all the time. All right. Cool. So this is basically the end of the first exercise. Again, everything is super, super simple, but this kind of Bex code is what I usually tend to do at work. You know, again, I don't do huge things with Bex. I just do small things that help me out. And yeah, this type of wranglers is basically what you would be seeing me doing all the time. Okay, I'm just gonna add a null. I'm gonna call this one out. And we could render this if we wanted to. We're not gonna render this now, but yeah. All right, so this is the end of the first exercise. We're gonna jump now. Okay, so let's start with a new exercise, or second exercise of this video. Let me save that here. All right, so we have a scene to play with. Let's do a little bit more work related with simulations. So let me create a geometry context, go inside, and I'm going to create this circle here. All right. I'm going to set that one to open arc. So basically it is a curve. And let's divide this a little bit more. So something like 50 subdivisions. Okay. Let's add a polywire, and this polywire, be careful when you add a polywire because everything needs to be stitched together, and as you can see there is a gap there, and that's because this is basically not closed. Easy fix with a fuse, right? We fuse those points that are you know, not farther away from each other from this distance. So now we should get that thing fixed. Okay, great. I don't need UVs here, so let me just ignore that. All right. And the next thing that I'm going to do, let's make some kind of torus. And you might be wondering, let's make a torus? Yes. But the reason that I'm doing it this way is because I want to use this curve. So if I start with a torus, I would have to extract the curve. So, you know, I mean, both ways are fine. I just prefer to do it this way. Okay, so this this polywire, let's make it bigger. Let's try 0.5. And of course we want more divisions. So we have like a nice rounded torus. All right, great. So we have that, and then we have this curve. So we can emit from those. Cool. Let me also create a polyframe here on the side. Okay. And in this polyframe, what I want to do is, because right now, as you can see, these are the normals that I have. So I'm pointing down. So I'm gonna ignore this normal name, and then in the tangent name, I'm gonna set this one to normals. So now, as you can see, the normals are basically following the curve, which is nice, right? Because then we can emit particles kind of revolving around this torus, which is nice. Okay, So let's transfer those normals to the torus, right? So we can transfer from here to there. So let's do an attribute transfer. And let's connect the polywire here, and we want to transfer from there. So maybe put this on this other side. Okay. And then we want to transfer the normals. There you go. So now we get the normals of the torus also revolving around itself. Kind of the same thing that we had here, right? But now applied to the torus. You can see that the normals are kind of broken in the viewport. That's fine. Don't worry about that. We can change that for rendering. But actually, we're not going to render this geometry. This is just for emitting particles. So if you don't want to get distracted by that, just remove the lighting from the viewport, and that's it. We don't really care about that. Okay, great. So now we have normals. Cool. Revolving around the circle. Shall we subdivide this a little bit more just to get more stuff? Yeah, maybe subdivide it a couple of times so we get way more normals, meaning that we're going to emit from all those. Because basically we're going to do the same thing that we did before. We're going to manipulate the normals to create velocity. Okay. I'm going to add a point wrangle, and let's manipulate the normals to convert them into velocity. So the normals are going to be equal to, as we usually do, some kind of variation. So let's fit O1 this into a random function based on the PT number. Random, PT number. Okay. And let's create a channel float that is going to be the minimum. Another channel float that is going to be the maximum. Great. I missed a parenthesis here. There you go. Great. So let's enable that and set this to, I don't know, 1 and 4. So now we have a nice variation there. I don't know what values I'm going to use here, but let's choose 1 and 4 for now. Let's add a global multiplier for that. So same thing, normal multiplies or equals by another channel float that I'm going to call multiplier. Okay, great. Let's create that, set it to 1, and we had the same as we had before. Set it to 3, and now we have something much more powerful. Okay, now again, we'll come back to these values. I don't really know what I want to use, but let's use that for now. Let's put this here so it looks pretty. And finally, let's pass that information to the velocity. So if we say the velocity is equal to the normals, now we should have velocity in there, right? And we do. So that's great. Okay, I had a value of 3, I believe, right? Value of 10 will give me a lot of velocity. All right, let's test this out. Let me see one thing. Maybe I want to have even more information here, right? So maybe we can do, let's see how many points do we have here. Let's resample this. Let's remove that one and choose maximum segments and give them a lot, like 250 or something like that. So now we should have even more information. So let's take a look here. There you go. And now we have a lot of information. Actually, this is quite slow to display now, but it will look nice when we emit particles from this. Okay, great. What else do I want to do here? Let's randomize this even more, because now we're randomizing the normals and also the velocity based on these and that, right? Let's add some more randomization here. So we can do a point bop here, and we can introduce some noises, right? Cool. So let's go inside and let's choose whatever. Let's choose a turbo noise, connect it to the position, connect it to the color so we can see it. And this is basically what we get. Okay, let's expose these parameters. So I'm gonna expose the type, the frequency, the offset, the amplitude, and the roughness. Maybe that's enough. All right, so I'm gonna change these to simple noise, for example. And let's play a little bit with this. Oh no, something like that. That looks cool. So basically, I want to emit only from the white areas, right? So yeah, something like that. I mean, choose whatever noise you want to choose and play with it a little bit. Let's increase this a little bit more. Let's have some range there. Okay, that seems to be fine. Let's clamp it. So maybe we can do a feed range here. Feed range, okay. We can promote this if we want to, actually. So yeah, we can basically clamp this a little bit more. I don't know, something like that, 0.05. Okay. What else do I want to do here? Let's offset this noise based on time. So, whoops, what did it do? I changed something by mistake. Oh, the amplitude, sorry. So let's animate these, perhaps, so we can do time. So it moves. Maybe this is too fast. Let's play real time. No, might be fine. Let's multiply this by, I don't know, 1.5. Okay, that looks decent to me. All right, let's add a pop network. And let's change this to be dark. And let's remove the grid. So we have that. And boom, we are emitting from there. Great. Right. We want more points, right? So let's go here. Let's go to birth. And let's give it a bunch more, a few more points. So I don't know, add an extra 0 there. So we have more stuff going on. There you go. And this looks quite nice. I think these values that we're using here are probably too high. So we say, I don't know, multiply by 2 perhaps. Maybe that's too much. 1 and 2. Okay, that looks cool. Yeah, I think it's still too much. We still need to play with life expectancy as we did before. But let's randomize this a little bit more because, again, you know, this velocity is based on the normals, but they all have the same the same value, right, between 1 and 2. So let's play a little bit more with that. So here I'm going to create another wrangler, so we can randomize this a little bit more. Or actually, yeah, let's do an attribute randomize. Why not? Let's do this. And let's randomize the normals. And let's choose here inside sphere. So now this is how the normals look like. So, you know, they are quite random. And now we can do a linear interpolation between these that we had before and these. So then we can mix them appropriately. Actually, maybe we want to do that before the noise. Yeah, let's do it here. Because here we have this, and here we're adding this thing. Right, so let's do that, and then we can mix these two. Before the noise, before it gets animated. Yeah, so basically, how do we do that? Well, if we connect this one here, right, now we should be able to do this. Before we do any of that operation, we can say the normals are equal to a linear interpolation, lerp. We learned about this function in the previous video. And we can say the current normals and then point based on the second input. So that would be 1 based on their normals and based on the PT number. Okay. And then we need a mix. So we can create a channel float that I can call bias or mix or whatever you want to call it. I'm going to call it mix. Right. And I think that's really it, right? Okay, so let's do that. Let's create that. So if we take a look at the normals now, we're mixing it with a value of 0. So this is basically the same as we had before. Well, plus the multiplier and whatnot. But then if I increase this one all the way to 1, we get all this randomization, right? So now it's just a matter of mixing this in whatever way you want. So I'm going to give it not that much, like 0.1, for example. Let's simulate this. And now we get way more variation. Maybe this is too much. Okay. That looks better, right? Cool. All right, nice. So now we have a very nice velocity information in there. Right. Let's play with the life expectancy, right? So same thing as we did before. We have these, where are we? Life expectancy, right? The life parameter that we saw before. So let's add a pop wrangle. There you go, pop wrangle. Great. And we can do something similar to what we did before. So we can say the life is equal to a fit01. Let's create a channel ramp to favor one or the other. So channel ramp, same thing as we did before. Let's call it ramp. And then use a random function based on ID. This is exactly the same thing that we did before. And then we need a channel float that is going to be the minimum value. And then we need a channel float, and this is going to be the maximum value. Okay, let's create all of that. Let's expand this ramp, and let's give it some kind of values here. I don't know. Let's give it like, I don't know, 0.15 and 0.8. Let's play this. Cool. That's nice. We might want to play a little bit more now with this thing that we had here. So I'm going to multiply by 3 perhaps. Okay, that looks quite nice to me. All right. And then we have this curve here, so we can do whatever we want here, just to even randomize this a little bit farther. I don't know, something like that. Let's see what we get with that. All right. Cool. All right, I like it. Great. What else do we want to do here? I don't know. Let me see what I can do. Let me go inside. And let me add a pop force, same thing that we did before, right? Great. And let's change, what do we have here? Maybe we can add some turbulence or some attenuation. Well, let's keep it as default. Let's add some drag, which is usually a good thing to do with particles. Let's increase this air resistance to something like 3 and see what we get. Right, so now, you know, the air resistance is too high, so this cannot really travel too far away. So let's manipulate that a little bit better. What can we do here? Well, I'm going to set it back to 1. I'm going to enable Beck's expression, and then we can use something here. So the air resist is called air resist. Okay, so air resist. And I'm going to base this on the H attribute that I showed you before. So let's say NH. Okay, so this basically means that, you know, there is more air resistance when they are born and less air resistance when they die, because, you know, it's based on the H attribute. And that makes sense, right? Because I guess the particles would be weaker when they are older. So that makes sense. All right, cool. Let me add way more particles, so we can add maybe another extra 0 there. Is this going to be too slow? No, it's actually quite fast. Okay, so that's looking nice. Do we want to change this a little bit more? 0.25, something like that, so we get more variation. Yeah, that looks probably better. Maybe I want to multiply it even more. Okay, that looks nice. So we have a very nice variation here, but at the same time, we're kind of following that star pattern. So that looks very nice. Okay, cool. So I'm gonna set my timeline to actually 100 frames. We don't need more. Okay, great. This looks fantastic. All right. Let's try to render these somehow, right? Because we haven't talked about rendering that much. It's not that important, but, you know, it's always good to kind of see final results. So I'm gonna add a point wrangle, and in order to render this, we need some kind of scale, right? So we're gonna use the P scale, and as usual, we wanna fit this, fit 01, based on some random function, based on the ID, right? Now we're talking about simulation, so we don't rely on PT number anymore. We rely on ID. All right, let's give it a channel float that we're gonna call min, another channel float that we're gonna call max. Great, let's do that. Cool. So now we have some scale. So later when we do a copy to points or instances or whatever, that would be applied. I don't really know yet what we're going to do, but we need to play with some small values. So I'm going to say 0.005 or something and 0.1. That will make a drastic randomization there. And let's also control the color. So again, we're going to use a point wrangler, and we're going to say that the color is equal to a vector based on a ramp. So I can create a channel ramp that I'm going to call ramp color, and based on the CD. Okay, let's do that. Let's create that. And now we are basically doing from black to white. So let's use some RGB values here. So this one would be perhaps blue, and let's add another one in the middle. And this one is going to be green. All right. Oh, what happened with the first one? I want it to be like that. Okay, so now we have red, green, and blue. We don't have that much blue, so maybe we need to push it a little bit more. There you go. So now we have a little bit of everything, right? Red, green, and blue. All right, yeah, that's a nice distribution. I like it. Why not? All right. Why is this complaining? It's looking for a float. How come? I'm using a vector here. Okay, well, never mind. It's a warning. The thing is working, so never mind. What else do I want to do here? Let's do a copy to points. I'm gonna enable instancing. Let's pipe that one there. Let's create a box and let's pipe that one there. There you go. And now we have this thing. All right. It is working, but all the boxes, let me enable lighting again, are kind of facing forward. So let's change that a little bit. I'm going to add an attribute randomize. And let's randomize the normals. There you go. So now we have everything randomized. We can use inside the sphere perhaps. There you go, to get more randomization. So now all those cubes are randomized. The P scale though is okay. Let's make it a little bit smaller. No, that's too small. Oh, okay, let's do this. Let's change actually the scale based on something else, because this doesn't really look that nice. So I'm gonna do this. I'm gonna say P scale multiply or equals based on itself minus the NH that we already know. So they are gonna get smaller based on their life. There you go. And this looks much better now. So basically, yep, there you go. Yep, they get smaller when they are dying and bigger when they are born. Okay, great. Let me animate these before being simulated. So before the actual simulation happens is where we want to do animation, right? So I'm going to do it here when we don't have any animation yet. Don't get confused by this noise. Remember that the normals are kind of broken here. So if you remove the light is where you see them happening. So I'm going to animate this. I'm going to add a transform. And I'm going to move these -5 units there. Let me display my viewport. There you go. I'm going to add another transform. And now I'm going to rotate these on what? Yeah, here. So let's assign a keyframe here and let's go to, I don't know, 36 and let's do -90 and assign another keyframe. So we have that. We have this animation. That should create like a nice trail of particles. Let's see if we need to cache this or not. We might have to. Okay, that's pretty cool. I think that, let me go back. Let me go here. Yeah, that's cool. But yeah, that's cool. But can I make this a little bit more distinct? Let me go here and let me do, I think that's fine. Maybe this is too much. Okay, something like that. Maybe this is too much. 0.05. Now it's too little. Just trying to find a good balance here in my simulation. Okay, let's see how that looks. Okay, yeah, that's okay. Yeah, I mean, it's not a big deal. So we get this nice trailing. Cool. Yeah, I mean, that looks nice. I'm gonna try to fix this banding by increasing the substeps in the simulation. So I'm gonna say the minimum substeps should be something like 3. Let's play again. Oh, there is one thing that I forgot also. To get like, right now, if we render this, we're gonna get motion blur based on the velocity, but only it's gonna take into consideration the actual simulation, but not this simulation. In order to get that properly, we need to go to the what is this thing? Birth interpolation source. Here in the birth, we need to set this one to forward. Now it's going, and we need to set this one to match topology. So now it's going to create those vectors based on the actual animation of this torus. It takes a little bit longer to compute, but it'll be worth it. Okay, so now we have this kind of weird simulation, and then we have this kind of star pattern. Let me go to the last frame. All right, I'm gonna create a camera, like maybe here. So let me create a new camera. Okay, so now we can render this. It's actually quite fast. Cool. All right. So what else do I want to do here? Okay, what if we wanted to render these in Solaris? Because if we want to render this here, yeah, no problem, right? Just enable this guy and just render it, and it will render just fine. But if we want to render these in Solaris, wait a minute, I'm not sure if I want to keep this one inside of sphere or just a constant value. I think I'm going to keep a constant value. Okay, cool. So let me go to frame 100. And yeah, I was saying that if we want to render these in SOPs, or I mean in here, if we go to OBJ and we create, OBJ, no, out. Oh my gosh, out. If we use our Arnold render or Mantra render or whatever we want to use this for rendering, yeah, that's no problem. But if we want to render this in Solaris, and you know, I don't render things outside of Solaris anymore, this needs to be replicated in LOPs. So basically, I'm going to add a null here, and I'm going to call this one out particles. And this is what I'm going to be rendering in Solaris, not this, okay? So let me jump into Solaris. Okay, and here in Solaris, I'm going to do a SOP import, and let me import my particles. Where are they? Here. I'm going to change the background to be dark. I don't want to see the grid. Let me also import my camera. So now we have the camera here as well. Okay, so here we have our simulation. Everything is working. Great. Okay, so let's add, well, we don't really need lights or anything really, just for testing. So if we render this, Well, actually, let me add some render settings. Let me connect my camera. And let me disable depth of field. And motion blur, if you want to get motion blur, right now we don't have motion blur, right? There you go. We don't have motion blur. We need to enable velocity blur and instance velocity blur. And now, as you can see, we have motion blur, right? So now this is working. Great. And as you can see, it's rendering spheres. And even though no one told Solaris to render spheres, or actually someone is telling Solaris to render spheres, but we didn't do it, but it's happening. And you know, the colors are working, the P-scale is working, so everything is working in that sense. How do we change that? Well, we can use render geometry settings. Pipe it here, select our object, and if we go all the way down, geometry, in this geometry section, as you can see, it's rendering points as spheres. That's what is rendering these as spheres. But if we choose something like disks, oh, and this actually doesn't work. This should work. Oh, I think this is probably an XPU thing. Let's try CPU. There you go. So now you can see that it doesn't work with XPU for whatever reason. So I can render spheres, I can render disks, or I can render oriented disks. So this is how you would change what type of geometry you want to use for that particle simulation. But of course, you are limited to whatever is here. Most of the time, most likely you're going to use spheres, but in our setup, we're using cubes. How do I use a cube if it's not available in this drop-down menu? Well, let's ignore this for a second. And basically, we need to replicate what we had in LOPS. So I'm going to disconnect this guy from here, put it aside. And what we can do is actually create a copy to points here. This copy to points is basically an instancer. So, you know, you can do instancers and that would be the same. It only changes, you know, your name. But anyway, so I'm going to use a copy to points. Very important. Don't use instanceable reference, because this is going to take very long time and potentially it can crash. But even if it doesn't crash, it would be very inefficient. So I'm going to set this one to point instancer. Okay. Now inside we have this thing. We can delete it. We can do an object merge, and we can bring the particles. So let's go here and choose our particles. There you go. So now we have particles. Great. And now we need a prototype to be instance. So if we take a box and we pipe it here, we have the same thing that we had before, right? But now it's been done directly in LOPS. So if I connect that one there, now we have our camera, we have our render settings. So if we render through that camera again, everything is working as expected. So the colors are being transferred. I mean, all the attributes are being transferred. The color, the P-scale, the motion blur, everything should be working here. Okay. Yeah. So everything is good. We can render without motion blur or with motion blur. Okay. Yeah, that's pretty much it. That's how you would render your particles here in LOPS. Okay, so either you bring the thing and use our render geometry settings, or if you want to instance some other type of geometry, you would use an instancer or a copy to points subpoint instancer and just pipe your prototypes. And at the moment I only have a cube. That's what I wanted to achieve. But if you would have multiple prototypes, you know, this is just an instancer. I show you in many other videos how to use the prototypes and how to choose multiple primitives and whatnot. Okay, great. Right, is that everything that I want to show you here? Yeah, I guess so. Yeah. So that's basically how you do this thing. let me go to build, and that's pretty much it. I don't know, something you can do here. If you want to render this in another way, you can do that. I don't know, maybe you want to convert this into a mass of BDBs or something and just render it as a single geometry. It will be a little bit expensive to fusion all these boxes, but you can do that as well. But yeah, this is basically the second exercise that I wanted to show you, right? Cool. So very simple, but you know, again, one of those things that we're going to be doing all the time with Bex. To recap a little bit, we controlled normals in order to create velocity. We added a little bit of breakup. Same thing here for p-scale based on NH. We tweaked the color here based on some attributes, and then inside of the popnet, we did things like a pop wrangler to control the life expectancy or any other force, and the pop drag as well to control, in this case, the air resistance. So as you can see, I'm just kind of going through random stuff, you know, like random attributes, just to show you how to use them. But, you know, again, you can use any. Okay, third exercise, and this will be the last one. This one is a little bit more complex. So we're going to be talking about matrices and vectors. Yeah, again, you would need some deep knowledge about maths. So there are certain things that I'm not really going to explain because, honestly speaking, I don't really understand very well because I'm not a math person. But I'll be going through the code, and hopefully you don't get lost. You would have to research a little bit, right? You would have to Google or to go to the Side Effects website and search for vectors and matrices and some of the stuff that I'm going to be typing here. Because again, if I need to spend the time giving you all the background and how the math works behind matrices and all of that, yeah, that's going to take me more than 2 hours. Okay, so let's leave that aside and let's start building this thing. So I'm going to create an Alembic thing here, and I'm going to call this one character. And if I go inside, I have a character animation ready for you guys. So if I go to ABC attack, I have this character. So this character is basically doing this. Oh, wow. Let's enable real time. Right? So this guy is basically, yeah. Wait a minute. This is 60 frames, I believe. So I'm going to set that one to 60 frames. So yeah, basically this guy jumping and it does that, and that's it. Okay, so this is actually something that I downloaded from Mixamo, but it's just an Alembic. I don't have any information about transformations here, right? So if I go to my geometry spreadsheet, yeah, I can see that things are moving, but that's it. I don't have access to that because this was not animated in Houdini. This is just a cache. So this is a very common production issue. You're working on a movie or something, and all of a sudden you get a character animated, a character animation that has been animated in Maya, because most visual effects pipeline rigging and animation happens in Maya. And you're an effects person, or not necessarily an effects person, but someone an artist or a TD that needs to do something in Houdini. How do you do that, right? Let's say that we want to take this sword, and when this character hits something, I think it's around frame, let's say 28. Let's say in this frame, we want to break the sword, or we want to emit some magic, or convert this into particles, or whatever. How do we do that, right? How do we access to the transformations of that sword? We can't, right? Because this is a cache. So in order to do that, we need to do something which is a little bit complex, which is generating two vectors that define the position of the sword, and then extract some matrices in order to pass that information back to whatever geometry we decide to use here. Okay, so let's try to do that. I'm going to unpack this thing so I can access to the geometry. I'm going to add a blast, and I'm going to blast the sword, and actually I'm going to say blast non-selected. So I have the sort here. I don't need to look at that. Okay, and I see that the normals are a little bit broken. So maybe we can create normals. So now everything works as expected. Okay, so we have the sort, it's being animated, but again, we don't really have information. I mean, we have the coordinates in the space, but that's not enough for us to play with this. Okay. So again, what we want to do here is extract the transformation matrix that describes how this sort is being moved, scaled, rotated, all of that. Okay. So the way to do that, first we need to create two perpendicular vectors. So basically, because two vectors will describe the kind of the position, right, and translation and rotation. So if we have a vector going that way and another one going this way perpendicularly, we can kind of compute the difference between when it's moving and when it's not, and then we can calculate those matrices. So let's do this thing here. I'm going to blast points, and I'm going to blast everything but the point number 0. So if I click on delete non-selected, you can see that here we have the point number 0, which of course is being animated, right? Cool. Right. So let's do that, because we only need to create that vector once. If we take a look at the normals or the vectors, there is nothing really there. So again, we need to create one vector this way, another perpendicularly that way. So I'm going to add a point wrangle. And let's put this aside, because basically I want the blast connected to the first input and the rest connected to the second input. Okay, so I'm going to enable this and template that so I can see where we are. So, you know, that's the point 0. It just happens to be there. It could be up here or down there, but point 0 is over there. So now I'm going to say the normals are equal to a normalize function. And this would be point 1, which is the second input, right? Based on, point input 1 based on the position of itself. Okay, and now I want to subtract the actual position of the point when I'm running this, right? So I would say minus at position. Okay, so if we take a look at the normals, there you go. Now we have that normal. Great. That will give us one vector. Now we need to calculate the perpendicular vector, right? So then we can define, with two axes, we can define the matrices. Right, so yeah, we have that vector for that point. Let's update this wrangler to actually interpolate between this point and the next one. So let's do this. Interpolation point 2, right? Because we're already using point 0, which is itself, and point 1, which is the next point that comes in the sort. So let's say interpolation point 2. Okay, now we can create a vector function that we can call whatever. We can call test vector. Yep, so we have that function. And then we can say interpolation the max points, all the points that we have there is going to be, this is just a name that I'm giving to the function, right? So integer function is going to be the max points, and that would be based on the total amount of points. You know this from before, that would be n points, okay? And the input 1, which is the sort. Okay, and that should be it. We don't see it, right? Because, you know, functions, we cannot see them. We need to pass that into an attribute. So if we say an integer attribute that I'm going to call test is equal to this function, max points. Okay, now we should be able to see that. So test is 42 points. And if we check the SOAR, it actually has 42 points. So that's correct, right? Because basically what we're doing here, yeah, that's fine. We got that vector for 1 point, but we need to run it over all the points of the SOAR. That's what we're doing here. Okay, great. Now, let's make some room here. Let's run that over all the points now to calculate the vector. So we're going to say for, and this is a for loop, so it's going to run over all the points. Integer, and we call that integer, how do we call this? PT, right? Before. Okay. This is equal to E, and we need to choose, it needs to be bigger than the max amount of points. So bigger than max PTS, that's how we called it, right? Max PTS, that's correct. And that's itself plus plus. Okay, and now we open the for loop here. And we say test vector, that's the function that we created before, is equal to, actually, wait a second. Are we doing this where? Yeah, that's correct. So text vector equals to the thing that we did before, right? So we're normalizing this again based on point. This is basically the same line that we had before. We can actually ignore it from there. One based on the position. And now we have the I here, great, and then we need to subtract itself, right? So if we do minus add p, there you go, that should work. Okay, we're getting an error because we're not closing the for loop yet. Okay, let me check that I didn't make a mistake here. Yeah, that seems correct. So basically now we say if one minus the absolute, well, we need to use the dot function. And again, you need to Google those functions, the absolute, the dot function. This is new, and what else is new here? No, I think we talked about for loops. You probably need to Google a little bit about for loops as well, right? Because it's a bit complex to explain everything here. So just follow my code for now, and you will see what's doing when you say it. It's probably better to understand when seeing it. All right. So dot, this is based on the normal. We need to run it over the test vector that we created before. And again, this should be bigger than the collinear threshold, and this is the threshold that is going to break the vector. Okay. Okay, great. And then we say up, this is the vector that we need to create, is equal to normalize. I'm probably missing something here, but I'm typing from memory. Okay, so that should be you should cross it with the normals based on the test vector. Okay, and then we have an integer point is equal to I, and otherwise it should break and just give us the vector. Right? I hope that's correct. We close that conditional here and there. All right, so let's see where we made some mistakes here. So if I cut all of this is working. So I definitely have a typo somewhere. So let me double check everything quickly. Right, so I think I forgot to actually add this collinear threshold function here, and again that should be a float collinear threshold. There you go, and now this seems to work. So basically what we're doing here is running over all points and just creating that up vector which is perpendicular at this normal. So if we go here and display the up vector, oh, Is it working? Yeah. So as you can see now we get like this vector, which is the normal, and the new vector, which is perpendicular to that. So that gives us an axis, and that should be enough information for the matrices to work with. Okay, great. Let's do the effects work now. So I don't want to display that, and I don't want to display this up vector anymore. So here we have the animation. Let me do one thing. I'm going to add a time shift here, and I'm going to say I want to time shift it to frame 1. So now we have a static sword. It doesn't move anymore, right? So here we still have the animation, but here we're freezing that animation so we can do the job. This is what is called a rest frame. Okay. I'm gonna scatter some points, maybe not that many, maybe something like 50. I'm gonna remove relax iterations. All right, all right, I'm gonna remove points at the bottom. So I'm gonna set this one to points and just select, I don't know, something like that. Cool. And now I want to break this, right? So I'm gonna use an RBD material fracture. Connect connect that one here. I'm gonna choose only one level of fracturing, and I'm gonna connect this one to the extra points and enable input points. So now when I do that, this should break. There you go. And if we want to take a look, this is how it looks, right? So basically we're breaking this thing. I don't know, maybe you want to give it a little bit more detail. So I'm going to enable edge detail, maybe make this a bit higher, something like that, and maybe some interior noise as well. There you go. So now we get this nice fracturing here. All right, great. So let me take a look at the animation again, because we said before that we want to break this when it hits. So what frame is that? Maybe this one, 28. Okay, great, 28. Put this on the side. We don't really need this. This is just for checking that this is working. All right, so I'm going to ignore that for a second. Okay, so basically we need to pass this animation to this fracturing, and then we want to enable the fracturing only when it hits the surface. Okay. And again, we cannot just pass the information. We need to create the transformation, and that's when matrices come into the play. And in order to use those matrices, first we had to create these vectors that we created before. Okay. So we need to create two different matrices, one for rest pose and one from animation, and then we want to combine those. So after this point wrangler, we need to time shift it again to frame 1, so it doesn't move, and that will help us to create the rest matrices. Okay, so I'm going to add a point wrangler. Okay, and I'm going to assign this time shift to the second input, the fractures, which is where we want to pass the information, to the first input, and this point wrangler that contains the animation, right? This is animated, to the third input. And now we can basically work with that, right? So again, we have the animation, we have static frame, and then we have a static frame as well of the original geometry. So again, now we need to create those matrices. Let me make some room here. So let me maybe add some comments here. So first we need the rest matrix. So we're going to say vector that we created before. We calculated the vectors here. Now we need to manipulate them here. So I'm gonna declare a new vector function. So vector that I'm gonna call rest normal, because we need the normals, we need the up vector, and we need the position, right? So this is gonna be point 1, meaning the fractures, right? So point 1 based on the normal and based on the first point. Okay. And now we need the same for the up vector. So let's just type up and up. And let's do the same for the position. Okay, great. Now we need to create a matrix based on that, right? So let's do here, let's do matrix. Let's call it rest M. That stands for rest matrix. You can call it whatever you want. And we're gonna say look at, which is another function. You can take a look at this in the Beck's dictionary, but basically it's going to look at something. And this is a vector. So let's say 0, 0, 0, because this is rest position, meaning that the position where it's resting, where it's 0, 0, 0, and this should be a vector like that. 0, 0, 0. There you go. And this is this needs to look at where? At the rest normals and the rest up. These are the vectors that we created before, right? Okay. And now we actually need to translate it. So we can use a translate for the rest position based on the same thing. Point 1, meaning the static frame of the fracture. So that would be based on the position and based on the first point, right? We only need 1 point. What happened here? Sorry. What did I do? Translate. Rest M. Okay. And rest. Yeah, sorry, my bad. Translate this based on the rest matrix. Yes. And the rest position. Right? Yeah, it should be like that. Yeah, okay. Rest matrix and the rest position. There you go. Yeah. Okay. Yeah, so basically what we're doing is we're declaring the vectors, right? Normal, up, and position. And then we're creating a matrix. And in the matrix, we're saying look at the normals and the up vector. And then move it based on the position. Okay? Yeah, we need to do it in 2 lines. Okay, so this is the rest matrix. Now we need the anim matrix. And that would be pretty much the same. So we can actually copy all these and we can paste it there and then we can just modify it. So this would be anim, this would be anim, and this would be anim. And here we need to take a look at the animation. The animation is the second input, meaning the third input, right? So this. So here we say 2, 2, and 2. And then here we create a new matrices, and this is the anim matrix. Okay. And this should actually be also looking at now the anim normal and the anim up, and now it needs to translate the anim matrix based on the anim position. Great. Nothing still happens, right? We just created the matrices. Now we need to combine them. So let's put here combine matrices. And now we take the rest matrix, and this should be equal to the invert of itself, right? So the invert of the rest matrix. There you go. So now we say matrix that we can name whatever, M, is equal to rest matrix multiplied by anim matrix. Okay, great. And finally, oops, my bad. And finally, we need to pass the position as well, right? Because right now we're just doing the lookup basically. So now we say the position is equal to multiply equal to this matrix M. Hopefully this works. Let's see. There you go. So let me check here. Okay, and there. Yeah, okay. So now this is actually moving the sort that we created here, right? So here we have this sort, and actually, you know, if you want to see it better, if you do this, we can see it better. That is the fracture sort, right? Great. Oh, this is stressful to write. And again, there are a bunch of things new here that again I wouldn't know how to explain properly, so just check the documentation for that. The good thing is like this is a very common thing in visual effects, right? So most likely you wouldn't have to write this, or you can just write it once and then just save this as a preset or HDA, whatever, and then you can reuse it all the time. All right. Now, we're not done yet, right? I mean, we're done transferring the animation, but now we want to break this at frame 28 when something gets hit. Okay, let's do that. So I'm going to add an assemble so I can pack the geometry. So create pack primitives, and I don't want to create new names. I want to stick to the names that I had before. This is still working, right? And if I unpack it, we still have the fracturing. So that's good. Now, let's add a DOPNet. I'm packing it because, you know, we're running this over a DOPNet, and in DOPS we need pack geometry. So let's go inside and let's create an RBD pack geometry. And I'm going to set this one to first context geometry, which is, you know, whatever we have connected to the first input. All right. So we have this guy now here. Great. It's not animated there, right? Because this is just a simulation context. And so, of course, that's not going to work. We need to pass the animation to the simulation. So we have the RBD pack geometry. I'm going to add rigid body solver. Okay, let's connect that one there. And we need some kind of gravity as well. So let's add some gravity here. And let's add some kind of ground plane as well. Let's merge it here. Let's put that thing first. Okay, and what if we press play now? Okay, so if we press play now, we get the simulation. Great, that's what we want, right? We want to fracture this based on some kind of contact. That is working. The problem though is that where is this animation, right? We need to transfer that animation to the simulation. So let's see how we can do that. In the RBD pack object, this override attribute field is disabled. So I'm going to enable this, and this will give me active animated, and deforming. And those are the attributes that I need to use in a wrangler to pass the information. So I'm going to go here and I'm going to add a point wrangler. And again, these attributes are called active, animated, and deforming. We don't need all of them. I don't think we need deforming in this case, but anyway, we can use it anyway. So what I'm going to say here, we set frame 28 where we want to start breaking this thing, right? Yeah. So I'm going to say if frame, which is a global variable, it's bigger than 28, then do something, right? And that's exactly what we want. We want to do something after frame 28. Before frame 28, we want to keep the animation that we have in the character. So let's open this thing here, and we're going to say integer active, which is one of the attributes that we just saw, is equal to 1. So once we are past frame 28, activate the simulation. Before, it's going to be off. So, okay, active is going to be equal to 1. The other attribute was called deforming. So deforming is going to be equal to 0, right? And finally, we had animated is going to be equal to 1. It's going to be animated. Great. Let's close this thing here. And then we're going to do the opposite. We're going to say else, meaning that if it's not bigger than 28 frames, so before we hit the 28th frame, we want to do the opposite, right? Let's make some room. We want to do the opposite. So basically, active is going to be equal to 0, meaning it's not going to be activated. The simulation is not going to be activated. Deforming is going to be equal to 1, basically the opposite that we had before. And animated is going to be equal to 0. There you go. And let's close this thing. Okay. Let's see what we get here. There you go. Now we get exactly what we wanted to. Let me add a merge here, and let me take my character, do that, and connect that one there, and do something like that. So it's easier to see. So now we have this guy that basically, boom. Okay. Okay, great. Do we want to do something else here? Yeah, I guess we can use some constraints, right? Because right now we don't have any constraints set here. So if we take a look here, these are the constraints, these are the proxies, right? So I'm going to take the constraints. I'm going to call this one constraints, and I'm going to connect this one to the second input of the .NET. So now we can go inside, and we can add a constraint network. And we can add these after the gravity. Actually, yeah, I don't know if I want to do this. Yeah, let's pipe it here. Let's play a little bit with constraints. Why not? This is complaining because it needs some kind of constraint type there. We need a type of constraint that we want to use, right? And here we're using a glue constraint, which is basically what comes by default in the RBD. If you go to constraints, it's using a glue constraint, right? So we can use the same type of constraint connected to the second input of the constraint and network here. And And now we have the strength of that constraint. So if I set that one to, I don't know, 100, that's what we get. It's probably too much. Maybe we need to set this one. I think this is a multiplier. So if we set that one to 1, and you go, is it a multiplier? So if I do this, it shouldn't break. It does break. What if we do something like that? Now it shouldn't break. It breaks. Is this being ignored by the other one? Shouldn't be, right? Because if I set this one to 1, and now I set this one to -1, then it shouldn't break at all. Yeah, something is not right. Let me reset the simulation. Yeah, no. I thought this was a multiplier. Okay. Because if I set this one to -1, yeah, that's still breaking. Let me ignore that for a second. This shouldn't break. Come on, what's going on? This is set. Let's do that. No, that's just not possible. I mean, the constraint is set to -1. How is this breaking? Oh my gosh. Okay, never mind. By the way, I think I made a mistake, right? Because this constraint network, we should set this one to second context geometry. Maybe that was a mistake. But anyway, if this is set to -1, it shouldn't break. Okay, now it's not breaking. Great. Right, but if I do this, it shouldn't break either. Yeah. Oh, because this one is still fucking things up, I think. Oh my gosh, I don't know. Anyway, I'm gonna set that one there. That one there. Now it shouldn't break. There you go. And yeah, what I was wondering is this a multiplier? So if I set that one to 1 and I set this one to -1, it shouldn't break, but it does. So it's not really a multiplier, is it? Okay, never mind. Let's try to get something. Yeah, no, it is a multiplier. Okay, I'm a little bit confused about this thing. Okay, never mind. That's why I usually don't mix, you know, these presets. The RPD material fracture is just a way of doing it. I usually do with booleans, and then I do my own simulation here. Anyway, I'm not used to do that. But anyway, so if I set that one to, let's say, 100. Okay. Cool, that's good. Maybe a little bit more. No, that's too much. All right, so let's do 1. All right. Maybe what I'm going to do here in the RBD pack object, in the physical tab, I'm going to set this rotational stiffness to something a little bit higher, so it doesn't bounce around that much. Okay, that's cool. Maybe that's too much. 50? Yeah, no. 10. Okay, yeah, that I like it better. Okay, great. So finally, we take a look at this. We put a null. We call this one out. And there you go. That's our little soldier doing that. It looks decent. All right. So this was the third exercise. Again, a little bit more complex. You really need to go through, especially not that one. This one is not that complicated. This one is the one that probably is going to cause more headaches. This one here, that's the one creating the app vector based on the normal of the first point, and that one, and this one here is basically creating the rest matrix and the anim matrix and then combining both. This is an extremely common situation in production. Like you get an Alembic cache or a USD cache from another package and you need to do something there. First, you need to extract the transformations. Honestly speaking, if you work in a Visual Effects studio, you would have tools to do that, right? But it's always a good idea to write your own tools to learn a little bit more and see what's going on there. Or if you want to do something at home. So yeah, once you have this, you can wrap this into an HDA and then you can use it forever. But yeah, this is how you manage to do something like this. Okay, great. So that's it for this video. I don't know how long is this video now, but I'm pretty sure it's over 2 hours. So again, thanks very much for looking into all of this with me, and I will see you in the next one. Bye.